Welcome everyone to the final presentations of this year's University of Washington Data Science for Social Good program. My name is Sarah Stone, and I'm the Executive Director of the eScience Institute, which has hosted this DSSG program since its inception in 2015. eScience Institute serves as a hub for data-intensive discovery on the UW campus, helping researchers use data science tools and techniques to advance their discovery process. And this DSSG program is one of our core signature programs. Today, you'll hear from our 15 DSSG student fellows who come from universities across the United States and bring their diverse backgrounds and disciplinary perspectives to the program. They've spent 10 weeks, but it's felt like 10 short and 10 long weeks, I think. It's gone way too fast. Working in highly collaborative project teams that include an eScience data scientist and one or more project leads from partner organizations. After running this program fully remote for the last 2 years, this year we had a hybrid program with 2 remote teams and 2 in-person teams that joined us here on the University of Washington campus. So today we're going to start with the presentations from our remote teams, and we have a remote audience that's also joining us via Zoom. So I'll give you just a few logistical notes, and please bear with us as we navigate this, even though we are all deep in this Zoom space and in the hybrid space, as I'm sure we've all experienced, it can still be complicated. For the Zoom participants, please use the Q&A functionality to ask questions. We will have time for questions after each of the presentations. These questions and on-site audience questions will be reread into the microphone so that all audience members can hopefully hear the question and the response. So bear with us with that. But we're welcoming questions both from the in-person and from the remote audience. So I think without further ado, I will invite our heating loads team, which I'm looking around the room, and of course they're a remote team. So let me stop sharing my screen. Yes. And Nick, can you turn off your screen, please? Okay, and heating loads, you can go ahead and share your screen, and I'm just gonna switch the video so that you see the room view. Okay, go ahead. Sorry.
Hi everyone. Thank you all so much for joining us today, and we'll be kicking it off. So the first presentation is about the project titled Heating Loads in Alaska and Beyond, and I'd like to start off by introducing the team. We've got our team lead Erin, our data scientist Nick, and from left to right the fellows, myself, Philippe, Maddie, Shamsi, and Vidisha. We have affiliations with a number of institutions, including the University of Washington, the University of Alaska, Stanford University, and Carnegie Mellon University, and bring subject expertise in areas such as economics, engineering, public health, machine learning, and regional Alaska expertise. For context, global warming is the most pressing challenge of our generation. It is happening approximately 4 times faster in Alaska when compared to the global average. There's a huge and increasing urgency to decarbonize energy sources, particularly in Alaska. And in order to reduce the accelerating impacts of climate change, reductions in emissions are vital. And therefore, national and local decarbonization is critical. Our work initially focuses on Alaska's Rail Belt region. The Rail Belt electrical grid region is defined as the service area of 6 regulated public utilities that extend from Fairbanks to Anchorage and the Kenai Peninsula. Residential and commercial heating make up large parts of the contribution toward global warming. And a large aspect of reducing energy and heating use is first understanding the current state. And thus this project aims to drastically improve the way heating loads are estimated in Alaska. Alaska has unique needs and challenges relative to the rest of the United States. For example, Alaska has far less centralized energy a large culture of independence and much colder temperature in general. And so the lack of centralized energy information is a key reason for this project in the first place. And so therefore, we aim to fill this energy use data gap in order to better understand the current state of energy and heating needs in Alaska. We do so by taking a geospatially informed approach. This means we use large-scale satellite data to get information with high granularity. In preparation and during this project, we have met with various Alaska-based researchers and experts to gain a better understanding of the current state of energy needs in Alaska. We've had individual meetings with researchers from national renewable energy laboratories. We met with scientists and Alaska heating experts, and we also had group meetings with experts from the University of Alaska and other parts of Alaska who are very well versed in the current literature and scholarship. Our work is in contrast to that current scholarship and research being done, in particular in this region. At the moment, micro-level approaches, meaning very time-intensive, on-the-ground approaches, are the only ones yielding results. So this means researchers go to individual houses, take measurements, install meters, and wait for months for results. In contrast, our top-down large-scale approach allows us to estimate the heating needs for large parts of Alaska. This work has immediate impact since it will enable researchers to do large-scale calculations for all of Alaska, which is previously not been possible. Additionally, results can be used for immediate sustainability and decarbonization policy implementations. And lastly, this approach can be expanded to the greater Arctic region, which shares similar challenges. So our task was to create a model that predicts heating loads for buildings, whether that be commercial or residential, in Alaska, accounting for very local climate. And we start off by doing a focus on the rail belt.
So what are heating loads? For our project, we define heating loads as BTUs per year and alternatively as BTUs per year per square foot. And a BTU, because many aren't familiar with that unit, it's a British thermal unit, and one of them is roughly equivalent to the energy released when you burn a match. And for reference, a heating load for a 1,500 square foot building can range between 45 and 90,000 BTUs per year. So that example I gave, there was a range of heating load, and that's because there are a lot of things that contribute to how much heat it takes to heat a given space. So for the purposes of our project, we went with these 4 variables that we would need to be able to estimate heating load. So the first is local climate conditions. This is pretty intuitive. If it's warmer out, there's less energy needed to heat your home. And we also needed the height, the base area, and the age of a building. What you'll notice about all 4 of these is that we can approach them geospatially. So that lets us use that large scale approach that Philippe described. A very broad flow chart of the process we're embarking on. First, we take building features, that's the building age, height, and footprint. We add to it climate features that we generate out of many years of climate data, combine them into a sort of model, and the output from that model will be heating load in the form of BTUs. To go a little bit deeper into the work, we're actually using a supervised learning model. So supervised learning needs output data to train on. Here, that's heating loads. And as Philippe described, there is no ground truth estimate for heating because that work is very, very challenging and we don't have it for large regions. What we do have are current estimates from researchers that have created regression equations for both Anchorage and Fairbanks to give some sort of continuous BTU estimate for buildings in those cities. So how does our model learn? So what we do is capitalize on the climate differences between those 2 cities, which as you can see are in different regions of Alaska. And then we generalize to the rail belt that has all sorts of different climate variation.
The extraction of building features from geospatial data was one of the biggest and most challenging aspects of our project. For this, we used Google Earth Engine, which is a cloud computing platform that allows one to access and analyze geospatial big data. The public data sets we used from Google Earth Engine's archive consisted of satellite images captured across time, as well as geometries of building outlines in Alaska. We had to aggregate these data, both temporally and spatially, to arrive at building level features, and then export these as tabular data for analysis. The next slides describe this process further. A key advantage of using geospatial data is that it not only allows us to identify where buildings are, but also estimate their ages and dimensions. A building's age or year of build may be important for estimating heating needs, as it may be correlated with air leakage. We estimate a building's age using data that tracked changes in land vegetation since 1985. Similarly, a building's height and base area determine its volume and thus may affect the amount of energy required to heat a building. While building heights were calculated using land elevation data, areas of building bases were estimated from building outlines. The shapes shown in orange in the map on the right are examples of building outlines we used. An important aspect of our model is that it uses local climate variables to predict heating needs of a building. The climate around a building is likely to influence its heating needs, and local climate may vary significantly within a state. By mapping land surface temperature data over building outlines and aggregating them over time, we construct heating and cooling degree days for each building. Degree days are simply measures of how cold or warm a location is. The more extreme the outside temperature, the higher the number of degree days, resulting in higher levels of energy use for space heating or cooling. The map that you see on this slide is a zoomed in version of the annual heating degree days mapped over Alaska. The variation in colors on the map correspond to the variation in local climate observed in the state. Pink denotes higher absolute value of heating degree days, that is, areas which need more heating. While climate is subject to cyclic fluctuations over time, the climate pattern observed in the recent decade may differ significantly from earlier ones due to climate change. Therefore, it is hard to say if more recent climate data or longer run climate variables would be better predictors of heating needs. As a result, using data from 1981 to 2020, we created 10-year as well as 30-year averages of degree days, which go as inputs into our model. With data on building features, climate, as well as simulated data on heating loads, we try to estimate a model that can predict heating loads at the building level. We explored a range of models, which include ordinary least squares, linear regression, ridge regressions, with and without polynomial features, decision trees, and random forests. We evaluated these models using their mean squared error on the test data. Each model's mean squared error is listed on this table, and one can see that it keeps reducing from top to bottom, showing that the random forest regression performs the best. A point to note here is that we are yet to explore a wide range of models and intend to do so as we get access to a more comprehensive heating loads database. On this slide, we try to explore which features are actually important in predicting heating loads as a part of the random forest that fitted our data the best. The y-axis shows various features which were included in the model, and the x-axis shows their importance on a logarithmic scale. Feature importance can be described as a score assigned to features based on how significant they are at predicting a target variable. From the graph, 8 seems to be the most important predictor. This can be expected as older buildings might be less energy efficient and more prone to air leakage. However, this may also be due to the output we used for model training, as it was interpolated from regressions of heating loads on age. We also see that heating degree days averaged over 1981 to 2010 and 1991 to 2000 are relevant in predicting heating needs. This highlights that it may be important to take both recent and older climate data into account while estimating heating needs. While these results are a part of a proof of concept exercise, they do have the potential to inform decarbonization policies like energy retrofitting in Alaska. For instance, the importance of the age variable as a predictor may answer if it is better to replace old buildings rather than retrofit them to save energy.
As Vidisha has shown in the last slide, we see that age and location-based climate data are the features that are most informing our models. As such, it's important to ask the question, what happens when we change how we're sampling these features? The basic idea behind data sampling is to balance the data that you're working with across a number of different factors. And the motivation behind this is to avoid biasing your model towards particular types of data. For example, in this project, we explored balancing our data over location and over building age. What this means is, for example, Anchorage and Fairbanks. Anchorage has a higher population than Fairbanks. As such, there are more buildings located in Anchorage than there are in Fairbanks. So without balancing our location-based data, our model is receiving more input on heating load needs in Anchorage than it is in Fairbanks. So to balance these, we upsample Fairbanks to make sure that the buildings coming from Fairbanks and the buildings coming from Anchorage are the same amount, so our model is not being weighted in any particular way towards location. From doing these results, we can compare what balancing location and balancing age and how that affected our different models. As we can see, balancing location improved the models, specifically the decision tree model and the random forest model, giving a much lower mean squared error for both of those models. And balancing across age, so making sure that we're passing an even distribution of building ages to the model, improved all of the different regression models. So we can see from this that balancing the data is definitely an important factor and can improve the heating load estimates that we're outputting. During this project, we have generated heating load estimates using our model that capture the variation in local climate. In addition to generating these estimations using past and current climate estimates, we also predicted heating needs for future climate estimates. All of this work is filling a vital information gap in the field of heating and decarbonization in Alaska, and can now be used to inform relevant policies and inform the way towards decarbonization in Alaska. Throughout this project, we've faced challenges, including challenges regarding the data and ethical challenges. For data challenges, the Arctic region specifically has particular challenges associated with collecting data there due to like specific regional weather patterns and things like that make it a unique area. As a result, our team has had to overcome this issue, and our solution was to take into account multiple different data sources for the data that we needed for our model to combat the fact that many of the data sets we were looking at were sparse in certain regions. In addition, we also encountered some data-related challenges while using Google Earth Engine. While Google Earth Engine is a great tool for large-scale geospatial analysis, the number of buildings and building features that we were looking at in this project is particularly large. We were looking at over 100,000 buildings and approximately 10 features per building that were quite detailed. As a result, we faced some challenges when trying to export the data from Google Earth Engine to pass it over to our model. The solution to this was to optimize the way in which we were exporting our data. Some of the ethical challenges that we faced on this project include the fact that we're working with large-scale geospatial data that's open source. Due to the open source nature of this data, it is impossible to collect any sort of community consent about the information in the data. And so, as such, as researchers in this field, we need to make sure to tread carefully and be transparent about how we're using this data. In addition, our top-down geospatial approach required assumptions as we went along. For example, our model assumes that the heat needed for the third floor of a building is the same as the heat needed for the first floor. which is most likely not true considering that heat rises and the third floor probably wouldn't need as much heating as the first floor. However, this was a simplifying assumption that we had to make in order to complete this project. These kinds of assumptions all require transparency on our part as researchers. While this project was only 10 weeks, its work is very important, and several of us will be continuing on the project. As such, we have a number of different tasks we'd like to see completed in the field. First off, we would like to incorporate the retrofit database that Vidisha talked about earlier. We think that incorporating this database into our model could tell us more about how effective retrofitting really is, and it could possibly affect how important the building age variable is that we saw in our feature importance analysis. In addition, we want to add more climate simulation models into our model, particularly those with higher spatial resolution, which will give us more accuracy and tell us a little bit more about the differences in weather between all of the different areas in Alaska. In addition, we did not have a chance to do a full sensitivity exploration of our models, meaning we didn't get to explore, for example, the assumption I stated earlier about building stories needing the same amount of heat. Finally, when talking to researchers about what they wanted to see come out of this project, one of the specific things that was noted was hourly heating load estimates. This is definitely possible to do from the information that we've gathered on this project and would not be too challenging, but it's a next step that we'd like to take in order to continue our relationship and collaboration with relevant researchers. Finally, other Arctic regions and the rest of Alaska can benefit from this work as well. It's very relevant and clearly important, as Philippe said, since global warming is one of the biggest problems of our generation. At this time, we'd like to thank our supporters of this project, the University of Washington, specifically the eScience Institute and the Data Science for Social Good program, and Micron. We'd like to thank all the attendees today for coming to hear about our project. We really enjoyed working on it this summer.
I see we have some questions already in the chat. I'll kick it off with a chat question and just flag me if there are in-room questions as well. So first, there's a great question. It says, how does this analysis factor in whether there are people living in the building or not? I think that would make a big difference. Does anyone want to jump in? I'm happy to answer it as well.
Yeah, I could answer that. Yeah, we haven't really accounted for whether people are living in the building right now, but yeah, that should make a difference. And yeah, as we said that we still, figuring out a lot of things, and yeah, the details are yet to be finalized. So yeah, that's a good idea. Great point. Thank you.
The next question is building age data available on Google Earth Engine? And what is the data source for your training data for heating load? So that's two different subparts. I can start with the, oh, go ahead, Philippe.
I was going to say, I can start with the first half of it. For identifying building age for buildings using Google Earth Engine, we looked at data sources that allows us to look at changes in vegetation amongst Alaska. And so identifying when kind of pixels and part of the image changed from being natural vegetation to having a building being started to being built is how we identified building age.
Yes, and then specifically the data sets were world settlement footprints. There was a historical multi-year one, there's a 2019 year one, and there was a dynamic Earth data set that we also looked at for present day. And then the other part of the question was about training data for heating load. I believe that came from an Alaska Housing Corporation report from 2014 that had those regression equations.
Okay, we have a question in the room. Go ahead.
Given how important the height correlation
Okay, so given how important the height calculation was, can you give an estimation of how you got the height and what the uncertainties are around it? I captured that.
Sure, I can take this question. So in order to calculate building height, we use two different data sets from Google Earth Engine that capture elevation data worldwide. So the first one is elevation with things like building and vegetation removed. So you can think of it as ground elevation. And the second one is elevation without those things removed. So with buildings and with vegetation. So the basic method was to subtract these two things and reduce over the building outlines. There's definitely some uncertainty in this method, as the data sets that we were using did not have the highest spatial resolution so particularly for very small buildings, it's possible that these estimates were not particularly accurate. I think that's one part of our model that we would definitely be interested in improving and are still exploring the best ways to calculate this and minimize that uncertainty.
I think we might have time for just one more. I'm going to combine two questions in the chat. One asks if they're both about extra data sources. So one is about whether we corroborated our heating load model with methane or carbon dioxide emission concentrations in the areas. And the other asks about socioeconomic parameters, like census data to corroborate or to add to our models. I can also take the question. So we haven't validated our models yet. This 10-week program is a little brief. And now that we're all experts on this topic, we're eager to do things like validate. I think this is a great idea, but it's not something we've had time to try yet. And then the health data, the census level data is really interesting to me in particular, given my background. We've definitely thought about it, but it has not been done yet. It's a definite potential future direction.
Great. Well, thank you all so much. Let's give them another round of applause. Great work, you guys, and nice backgrounds. Okay, I'm going to invite the Satellite Streaks teams to go ahead and turn on your cameras and go ahead and share your screens.
Hello, everyone. Welcome to our final project presentation. We are the Satellite Streaks team. My name is Kilando, and I'm joined by the other two fellows here, Abhilash and Ashley. You can probably see them waving on the Zoom screen. We also have our project leads and data scientists, Dino, Meredith, and Vaughn, who are very integral in helping us accomplish this project. So today we will be discussing the problem, our project and its output, the process behind our summer project, and future work that we intend to impact. So at this point, you're probably wondering, what about satellites impact our ability to perform social good or mitigate social harm? And a lot of people may have this question because they're familiar with satellites as being revolutionary in many arenas, maybe revolutionary in the space race with the release of Sputnik by the Soviet Union, or revolutionary with the geostationary satellites that give us GPS navigation. And some people understand satellites to be integral providers of wireless communications and connections such as the internet. But a lot of people aren't really aware that satellites can and do inhibit human beings from being able to access the natural resource that is the sky. And the particular satellites in questions that do this are low Earth orbit satellites. So low Earth orbit satellites are highly reflective of the sun's rays, very similarly to how the Earth's natural satellite, the moon, functions. But unlike the moon, they rapidly orbit the Earth in the span of 30 minutes. And as such, low Earth orbit satellites are visible to the naked eye, posing a threat to nature, culture, and astronomers. In terms of culture, there are global indigenous populations that rely on the night sky as a traditional religious and cultural resource. And the visibility of these low Earth orbit satellites pose a threat to the integrity of this resource, especially since these traditions are passed down orally. In the words of Professor William Sutherland, in terms of nature, low Earth orbit satellites may mislead animals from responding to celestial cues. And in terms of astronomers and astronomy enthusiasts, I want to reemphasize that these low Earth orbit satellites are highly reflective and very fast in their orbits. So in order to demonstrate that, I'm going to show you all a visualization. And as you can see, there are flashes going across the sky here. And those are actually satellites that are visible. And as you can see, they're very bright and very fast. And when telescopes take images, they don't do so instantaneously, but they take a few seconds to actually capture the image. And so those satellites end up appearing as streaks. So to demonstrate what a telescope image would look like, this is an actual telescope image. And this image, as you can see, it has a few dots that represent stars and celestial bodies, but more importantly, it also has satellite streaks going across the image. And these satellite streaks makes it very difficult to just explore space for astronomers and for astronomers to also learn more about the celestial bodies that are surrounding us. So we also want to emphasize that the problem isn't just satellites, because satellites aren't inherently bad. As mentioned, they allow us to get great innovations. But the problem is the exponential launch of satellites by commercial aerospace companies. So as you can see in this graph, we have the number of untracked objects and the number of tracked objects in Earth's orbit. And as you can see, there's a general uptick of most of the objects. However, if you look at the blue line at the bottom that says active, this is representative mostly of low Earth orbit satellites. And as you can see, there's an exponential growth in the recent years of the amount of satellites that are being released into orbit. So if I have not convinced you of the gravity of the situation yet, I'm going to show you a simulation, and each of these pictures are simulations of the Earth, and surrounding the Earth are dots. And each dot represents a satellite, and the color of each dot represents the company that has launched or intends to launch the satellite in question. So in 2019, we see there are some, but not an overwhelming amount of satellites in the Earth's orbit. But in 2021, we see that there is an exponential growth, and this is the true amount just last year. And in 2023, although 2023 has not happened yet, these are estimations based on aerospace companies filing with institutions about their intentions to launch satellites. We see that there is a striking amount. And in 2025, the exponential growth is so visible that the Earth is covered with a cloud of satellites. And we also want to discuss the fact that there are no regulations on the brightness or numbers of satellites that are launched by these companies. So to reiterate the problem, there are a large number of low Earth orbit satellites, and as such, this creates streaks in astronomical images, making astronomy research for both astronomers and astronomy enthusiasts very difficult. So hopefully I've convinced you that the satellite streaks are definitely a problem. So let's examine how our team's project attempts to address this problem.
Great, thanks, Kilando. So with that overview of the problem, we believe that one of the first steps towards tackling this issue is sort of quantifying the impact of this problem, such as quantifying the properties of the satellites, quantifying to what extent do they damage the astronomical images. And that is specifically the motivation of our summer project, which is to detect and quantify satellite streaks in astronomical images. So in terms of the current work done on this topic, we have astronomers tracking individual constellations of satellites such as Starlink, and we have telescopes that regularly capture images containing satellite streaks. And what this data leads to is analysis of this kind where certain properties of the satellite streaks are quantified. However, one of the drawbacks is that these are mostly like bespoke, manually done analysis that cater to the specificities of that particular image or that particular telescope. And we want to take this forward by scaling up this process and making it more generalizable. So starting with the current body of work, we want to leverage computer vision algorithms and create a generalizable tool that can take in a wide variety of images containing satellite streaks from a range of telescopes on Earth and obtain basic information on these streaks properties. And as a next step, like there are many use cases for this basic information. One of them, for example, is that we know a lot of satellite operators are currently working on mitigation strategies to reduce the brightness of their satellites. And this tool could provide at-scale information to these operators on whether their mitigation strategies is working or not. So with that overview of like our goal, I want to present you our output from this summer project, which is a Python library called SatMetrics that can detect and quantify satellite streaks in astronomical images. We use an open data repository for astronomical images affected by satellites called Trailblazer to build this tool. So at a high and simple level, the SatMetrics library can take in like a wide range of images containing satellite streaks. And if like those images have a streak, then detect that streak and output basic information about the streak that can lead to further analysis downstream. And all of this is towards the hope that like generating more information and more analyzable information on this topic can draw more attention towards this problem and probably support like possible policy interventions towards this issue. So now I'm going to spend some time talking about our process of how we built this library. So at a high level, there are three basic steps that we follow to create this. The first one is detecting straight lines in images. The second one is validating those straight lines to differentiate them from noise. And once validated, like we want to measure the properties of those streaks. So I'm going to talk more about the detecting lines part. To begin with, like detecting lines or straight lines in an image basically means like finding which pixels in that image contain that straight line so that we can study the properties of those specific pixels. So we use a widely used straight line detection algorithm called Hopf transformation to build this tool. So over here in this image, it's an example image. It's binary. So all the dots that you're seeing are like the only non-zero pixels in this image. And essentially how Hopf transformation works is it counts the number of non-zero pixels on every possible straight line in an image. A possible straight line being a collection of at least like 2 points. And more the number of non-zero pixels in a straight line, the higher chances of the algorithm voting it as a possible line. So as you can imagine, with the existence of noise in an image, the accuracy of this algorithm goes down. So along with returning what actually is the streak or the straight line, it can return a bunch of like false lines that essentially just represent noise. And that is the key challenge that we deal with in this part of the process. So on the screen, you can see like multiple real astronomical images containing like a wide amount of noise and differing like noise to like, pixel noise to streak brightness intensity. And consistently removing noise in like these wide range of images so that we can detect lines in them is the biggest challenge for this step. So we use various standard image processing techniques to like deal with this problem. And I'm not going to go deep into like each of these methods, but I'm going to motivate all of these by walking through an example. So on the left, we have like a original astronomical image with like containing multiple streaks and a lot of noise in the background. As a starting step, we try to estimate the background in this image so that we can remove that from the raw image. So on the right, you see like the image where the background of the original image has been estimated and removed. And you can see like some reduction in the amount of noise. Once we do that, like we apply binary thresholding and adaptive blurring of the image to progressively reduce noise. And one of our key assumptions around these steps is we expect the satellite streak to be like on the brighter end of objects in that image. And finally, after applying edge detection, we apply the Hopf transformation algorithm. So you can see the image on the right, where we have like the straight lines being detected and returned by the algorithm. One of the challenges that we face that is again related to noise is sometimes when there's like a lot of noise surrounding like a satellite streak, we can have like multiple straight lines returned that essentially represent the same single streak, as you can see in this image. And to tackle this problem, we use like a clustering approach that I'm going to like demonstrate through like a different example. So on the left, you have like another example of an astronomical image containing a streak that does not go through the entire image, and you have a lot of noise surrounding that streak. And on the right, you can see what our algorithm returns as straight lines. So you can see that the actual streak line is returned, as well as a bunch of other lines are returned, which essentially represent noise. So we try to cluster these into groups, where each cluster essentially represents like either a single streak or a collection of noise. So on the left, we have the straight lines returned, and on the right, we have like successfully clustered it where like the actual streak is contained in a separate cluster and we have noise in a bunch of other clusters. And the reason we do this is because we have validation algorithms downstream that can separate like noise from straight lines, but we don't want to waste computation by running that algorithm on every single detected line. So when we divide it into clusters, we can apply that algorithm at a cluster noise and cluster level and like perform our validation. So I'm going to pass it back to Kilando to like speak more on this part.
Thanks, Abhilash. After we found clusters of Hoff lines that may represent a streak, as Abhilash said, we want to validate that what we've actually found is a streak. So to do so, we take the median pixel values of each row of an image and analyze the profile of that data. We look for key elements such as, is the fit of the profile approximately Gaussian? And if so, does that profile have an amplitude or a width that is characteristic of what we think a streak would look like? But before we can perform validation metrics, we have to rotate the streak. Our goal is to rotate all of the streaks in an image such that each streak is horizontal, and we crop those streaks so that they're the only streaks in the rotated image. So when Hofflines finds the streaks, they find them in polar coordinates. So we start by finding 2 Cartesian coordinates of the line. We choose 2 points, the point at which the line enters the image and the point at which the line exits the image. We use those 2 points to calculate a slope, and then we use some basic trigonometry to calculate the angle of rotation. But when we rotate the angle, when we rotate the line about the angle and the image, it only rotates at the center point of the image. And so it's very difficult to find where the rotated line actually is. So to mitigate this problem, we basically set an anchor point, which we decided would be the midpoint of the line. So when we crop the image, we can easily locate where the rotated image is and crop it so that it only contains the streak. In cases when there are more than one line in the cluster, we take the mean, entrance, and exit Cartesian coordinates and perform the same computations.
So just to reiterate, rotating streaks allows us to do efficient streak analysis. So now that we've figured out how to rotate the streaks, we can now take an image and plot its pixel intensity values. The point of plotting pixel intensities is to tell us what and where the brightest object is located in our image. We take the median of the pixels because since a streak is consisted of clustered and extended pixel intensities, it offsets any outliers and gives us a more obvious peak. So in the top image, we have a bright star with some background noise. We see that the pixel intensity plot on the right side generates very narrow peaks, whereas on the bottom, the peak is more obvious in that it represents the streak in the image. Because this plot looks approximately Gaussian, we use a Gaussian as our model to fit a line through it and determine whether or not we measured a streak. So here we give an example of what a bad fit looks like. In the image above, we see that there's no streak, but rather just some bright stars and noise. Because there's no streak, the plot of this image contains narrow peaks and doesn't look approximately Gaussian. So when we try to fit a line through it, it doesn't converge and due to not passing our validation. So we would throw this plot away because this tells us that we're not measuring a streak, but rather some background noise, which based on the image we see here is true. So this means that this data is not useful to us and we would throw this one away and won't continue property measurement on this image since there's no streak. So what happens when we do validate a line within an image? The next step is to measure the properties and extract the quantification metrics of the streak. So here we have an image of the streak and its pixel intensity plot next to it. The red line on the right side of the plot is our fitting line, and visually we can quickly tell we have a good fit since the red fitting line is very close to the blue real data line. But what happened here statistically is that the normalized root mean square deviation, distance from the middle, and full width half maximum pass thresholds that pass validation. And since it validated and converged, we can confirm that we've measured a streak. So in this case, we keep this data and extract all the quantification metrics that Kilando mentioned earlier. Another great benefit of fitting a line through our data is that we're able to use these metrics to help further the rotation angle algorithm. Sometimes when we would rotate the streaks using basic trigonometry, the streak would not come out completely horizontal, which would make the property analysis less precise. To straighten the streak, we rotate the angle on the Hoff transform line with new angle calculations that are pretty close to the original calculated angle. Once we have our new angle calculations, we have to test them to see which one is the most accurate one that straightens the line. So here we see only 6 rotated iterations of one image. We apply the fitting function on them and assume an image with the smaller normalized root mean square deviation is more representative of a straighter streak to help us make the rotation more accurate. Here on the we see on the last image on the bottom right side has the lowest normalized root mean square deviation, and its line is fitted very closely to the real data. Because we see this, this means that the angle calculation that we have for this image or graph is going to be the best one for our rotation algorithm and allows us to measure our streak properties with more accuracy. So with all the work done within line detection, validating lines, and property measurement, we came down to our StatMetrics Python library that successfully outputs quantified streak properties from the images. StatMetrics is a public Python library that is meant to be used by anyone interested in analyzing satellite streaks and images, whether that's an astronomer doing research on satellites or enthusiasts who took pictures of the sky, noticed streaks in their images, and want more quantifiable information on the streaks. StatMetrics does not end here, though. There's still further developments that are important for our package. But before we dive into that, here's a quick recap of satellite streaks and astronomical images. The initial problem is that the industrialization of space makes the sky brighter, which causes environmental concerns, disrupts cultural traditions for communities, and produces satellite streaks and astronomical images, which makes studying the stars, galaxies, and our universe more difficult for astronomers. In order to study how streaks affect astronomy, nature, and cultures that rely on the sky, we first need a standardized set of measurements and analyses tools to characterize these satellite streaks, which is what our StatMetrics Python library is, a tool that outputs standardized sets of measurements in order to further analyses of streaks and images. So the next steps are a working solution. It's important to measure the brightness of our streaks, which are characterized through magnitudes, which are astronomical brightness units that astronomers rely on. We hope to use the measured pixel intensities to convert into magnitudes so astronomers have more additional useful information of the streaks. This will also help with evaluating if the streaks would be visible to the naked eye. So far, we've only tested our data on a variety of streaked images from the Trailblazer repository, but we want to continue testing this by creating test data sets and continue measuring the precision of the metrics. And finally, our long-term goal is to integrate our Python library to the Trailblazer repository, so when someone uploads their streaked images, our library can generate quantified streak data. Overall, we're very excited that our Python library could aid astronomers or enthusiasts in the research of satellite streaks so that they can come down to more feasible solutions at addressing the overarching problem of satellites. Thank you so much for your attention. We will leave the summary slide up for your reference. We're open to taking any questions.
So we have one comment in the Q&A which says images from radio telescopes could use StatMetrics to measure streaks from non-low Earth orbit satellites, which is a great point, and like hopefully like something that happens downstream for like this library. So yeah, thanks for that.
Do we have, I don't know if you guys can see. Okay. Everything okay? Okay.
Okay, yeah. I think you cut off for like a few seconds. Could you repeat what you were saying?
I'm muted on here. Okay. Step away. I just wanted to say there were lots of clapping here, but we had muted ourselves because the sound quality was better. So I didn't want you to think that nobody clapped. There was lots of clapping. Are there other questions in the audience here or online? Jessica.
I would imagine that some end goal of this is to take satellite images and remove streaks from them. Do y'all have any ideas, or have you talked about what you replace the streak with in an image?
Oh,
is it just like black sky, or is there, what if there are objects behind it?
Okay, great question. So the question was imagining that part of the goal of this project would be once you identify images that have streaks to remove the streak, but then what do you replace them with? Am I capturing that, Jessica? In case if there's things that are behind them that are missed, essentially.
Yeah, thanks for the question. And yeah, sorry, go on, Kilando.
Well, I was just going to say, I think at this point in the project, that would definitely be a goal to work on discovering ways to potentially remove satellite streaks from astronomical images. But as of right now, we have focused mostly on metrics that would be useful to astronomers, especially brightness metrics. So we haven't, developed a way to remove the streaks just yet, and we haven't gotten that far in thinking about that process.
Yeah, and just to like add to that, I think that's definitely like a body of work that like astronomers around the world are currently working on. Another problem related to this that people are working on is just like, creating algorithms that can dodge the satellites. So setting, image timing such that it dodges the satellite. But like, as Kilando mentioned, I think like sort of in terms of our aim for this 10 weeks was just to like create the starting step tool that can like start making some of these like analysis generalizable and at scale. I'll also like continue with just like reading out a question from the Q&A section. So the question is, what is being done to clean up satellite debris, and or how would we do that? That's a great question, and I'll be honest, I don't know the answer. I think like in terms of what's being done from a policy perspective, it's like one of those like really like challenging international problems where like more than a few countries are involved and contributing to that debris. But right now, in terms of how to clean up the debris, I'm not sure like what are the exact steps that are being taken. But yeah, if anyone else from my team would like to chime in, I know Meredith maybe.
Yeah, I can chime in if you'd like. I just wanted you to know that I was here in case there were any particularly challenging questions. So I am an astronomer and not a satellite debris expert either. However, there are lots of discussions going on kind of how satellite debris fits into this larger picture of space pollution and how it affects lots of different things. We obviously focused on astronomy and streaks in this particular project, but it's absolutely true that the debris problem is a serious concern as orbital space gets more crowded and things are more likely to smash into other things and create even more debris, which could be like a runaway cascade effect that would not make space particularly useful for anybody, astronomers included. So the one pro in that particular scenario is that the satellite operators don't want that to happen either. So they are at least working towards solutions that enable them to have a precision knowledge of the location of their satellites and make sure that they can maneuver to avoid other satellites. But it only gets more challenging as the population increases.
I think we can do. I was just going to say we have time for one more question.
Sure. So I guess.
Go ahead.
Okay, go on.
Go ahead, Abhilash.
No, it's just like reading up a question from Q&A, which is that will it be published on GitHub? And like the answer is yes, with like some appropriate license, and like we're working on it, and like this will be like an open source repository. But yeah, Sarah, you can like maybe ask the question from the audience as the last question.
Okay, yeah, we'll take one audience question.
Are you linking the streaks that you're detecting to the satellite that caused them?
Are you linking the streaks that you're detecting to the satellite that caused them?
That's a great question.
Is that so you can get people in trouble?
Yeah, I actually like some drawing back to like the beginning of this project, I think there's like usually sort of some friction expressed within organizations and actually like identifying like the streaks and like telling which those belong to which satellites, because apart from like like low Earth orbit like telecom satellites, we have like a bunch of other government and non-governmental satellites as well. So we are not linking to which satellite those streaks belong to, but there are definitely like telescopes and groups of astronomers who track like specific like satellite constellations such as like Starlink constellations, and there in those images. So for example, some of the images that we showed, we know that those are Starlink satellites, but that's not like as an output of our work.
Okay, I think we need to move on to our next team, but let's give another round of applause that you'll hopefully hear. Nice work, you guys, and I'll welcome up the self-sufficiency team.
Oh, wait, it's not showing the right. It's not showing the right screen. Why is it not showing? Oh, thank you. Okay, there we go. Okay. And then go into full screen. Okay, good. Oh, wait, I'm gonna put that away for them. And does it?
Yeah. So hi everyone. Our DSSG project was titled Exploring New Understandings of the Cost of Living at a Basic Needs Level Using the Self-Sufficiency Standard database. So the fellows were Chang, myself, Priyana, Aziza, and Hector. And our project leads were Annie Kuklik and Lisa Manzer from the Center for Women's Welfare in the School of Social Work here at the University of Washington. And our data scientist was Brenna Hazelton from the East Science Institute, also here at the University of Washington. So I'm first going to start off by talking about the US official poverty measure. And so the official poverty measure sets eligibility for critical benefits such as food assistance, childcare subsidies, or housing vouchers. Many families, however, cannot afford their basic needs and are not considered in need by the US official poverty measure. And so how it's measured hasn't been changed since it was created in the 1960s, and it doesn't vary by place. So the poverty line is the same for Mississippi as it is for the state of Washington. So the self-sufficiency standard is a budget-based living wage measure that determines the amount of income required to meet basic needs at a minimally adequate level. And it was created by Dr. Diana Pierce at the Center for Women's Welfare to provide an alternative to the official poverty measure. And so it includes the costs for the basic costs for a budget, but it does not include luxuries such as eating out, and it only includes what you need to get by without the use of subsidies. The standard is calculated for 42 states here in the United States, and the Center for Women's Welfare strives to make the standard as consistent and accurate as possible. So the data used to impute the standard is calculated and collected using standardized or equivalent methodology nationwide. It's obtained from scholarly or credible sources such as the US Census Bureau. It's updated regularly, and it's geographically and age-specific as appropriate. So who utilize and interact with the self-sufficiency standard data? So community organizations, academic researchers, policy institutes, legal advocates, training providers, community action agencies, and state and local officials are just a few of the people who utilize the data. And they can use it as a policy analysis, a counseling tool, an evaluation tool, a benchmark for wage setting, targeted allocation of resources to further research, and also as a community indicator. So for this project, some of the community partners that we spoke to include the Workforce Development Council of Seattle-King County, and they utilize the standard to provide financial counseling to their customers. We also had conversations with the Colorado Center on Law and Policy, and they use the standard to advocate for better wages and to support employment. And in addition to our partners, we heard more from Dr. Pierce, the founder of the standard, who utilizes the tool to validate costs for testimony as an expert witness in Congress. And lastly, we spoke with our project leads, Annie and Lisa, who are researchers here at the Center for Women's Welfare, and which ultimately manages the standard and its data. And they were the primary stakeholders for this project. And so while we weren't able to speak with every partner, the Center for Women's Welfare utilizes has a breadth of partners who utilize the standard to further their work in their respective states across the country. While the self-sufficiency standard data is open and publicly available and also readily used by its partners, the workflow to transform the data is inefficient and hard to reproduce, and this makes it difficult to conduct deeper, more novel analyses. So the current challenge with the data is that it's spread across state and year in separate files and locations on the Self-Sufficiency Standard website. And while the files are extremely standardized, how the data is formatted makes it difficult for automated analysis. And this is, for example, because there could be duplicates or spelling errors. And then when conducting analyses, because they're done manually, it requires manual validation to check that everything was transferred correctly, especially when copying and pasting from tables. And because of this, it's difficult to track the workflow and the specific steps that are taken. And this evidently takes significant time to complete. So for reference, the Center for Women's Welfare conducts a city comparison, and we'll actually talk about that more later in the presentation. And right now that takes about 3 to 5 hours to conduct. And then lastly, another important thing to note is that these certain type analyses, such as the city comparison, are only conducted and changed by experienced researchers. So there's essentially a bottleneck in how many people can utilize the data and the standard itself.
So this leads us to our research question: how can we store self-sufficiency standard data to increase the efficiency for stakeholders to use the data and extract meaningful information and conduct novel analyses? So for this, we perform database development process, which actually consists of 4 main parts, including the preparation step. So initially, we conducted stakeholder meetings and further research to be able to understand the columns and their relationships better. So in order to store the data from all the files in one database, we preprocess the files to standardize the column names. Then we created the relational model schema that arranges the data in a series of tables, rows, and columns with a relationship between tables. And then we use the Python to read the data from the Excel files and do cleaning and pre-processing. So we use SQL Alchemy to create database tables and insert the data from the files into a SQLite database. So this is actually our final result for the database schema. So in the self-sufficiency standard data, most of the columns are consistent among files, but there are a few columns that contain extra information and they're only present in some files. So in order to increase the efficiency of accessing the data, we created one table with the data that is always present, and 3 helper tables, which are GeoIdentifier, CT, and PUMA, to contain extra information that is only sometimes available. We also added Boolean columns to the main table, which are healthcare, miscellaneous, and ARPA, to the main table to indicate when the extra information was available. And the report data, as you can see here, it's a data that comes from census. So as we all know, we need the primary keys. So our main primary keys were family type, state, place, and analysis type, that it was same across the main and helper tables to make it easy to link the data across tables.
So as we have like the supplement information that is not come from the original goal of this project, but during our discussion with our stakeholders, we kind of inspired by their ideas. We saw the possibilities that researchers can conduct other or supplement research and measurement based on this open data sources. So for healthcare, miscellaneous, and ARPA, as Aziza mentioned before, this data originally come from the self-sufficiency data set. And the PUMA city county, the city table, and the GeoIdentifier is come from the census HUD or CPI data set. Mostly for the PUMA, for example, the PUMA is the full name, PUMA is the short name of the public use microdata areas. And we link to the ACS data set, which is American Community Survey, a part of the one kind of the census data. And this data, this combination make it possible for us to compare, for example, the percentage, the population percentage above and below the self-sufficiency standards across some kind of like areas. And the city county, the city table, we refer to the city county crosswalk table, since most of the standards are county based. And if we want to compare the city, let's say King Seattle and San Francisco, we need to go back to see which county the city belongs to. So this crosswalk table make it more efficient to compare the cities about the self-sufficiency standards. The geo-identifier is easier for us and the researchers to compare the CPI and the inflation justice across by years when the CPI changes, and the report date is mostly for the log purpose when the database updated.
So one of the key goals and ethical considerations of this project was providing transparent processes for our project leads and our community partners with varying technical backgrounds. And this was to ensure that the workflow and analyses are reproducible beyond the scope of this 10-week project period. So to do so, we provided rigorous documentation of our code in the form of markdown files on our GitHub repository. And this was split up into two parts. So the first was how to set up your technical environment. And so this includes downloading the specific software and initializing the database. And the second part was how to insert and retrieve data. And so specifically how to pass files into the database.
And based on the documentation and improved workflow, those responsible for conducting analyses will be able to produce analyses which are now more reproducible because a lot of the operations are more automatic and less manual driven. And I'll give an example of how the workflow has changed before and after the database. And in addition, with the database, we, the fellows, were able to conduct analyses that were not possible prior to the creation of the database. So for the workflow example, we're specifically looking at analyses across cities, and we're interested in comparing similar sized US cities across time. And before the database, this was only done at one point in time, and it was across only one type of family type. As you can see in this map, there were only family types listed for 1 adult and 1 preschoolers, and the self-sufficiency wages needed for that specific family type. And this was the workflow to create the map just shown. The person responsible for creating this analysis would have to open 16 files, which was for 4 cities across 4 different years because of how the data is stored. And from there, click on filter settings to get the specific family type and copy and paste the rows of interest into a new file to create visualizations of interest. And overall, this workflow took about 3 to 5 hours to complete. However, now with the database, this process is a lot more shorter. And specifically, we would just call the database and retrieve the information and the information of interest and run our code. And this would take 5 minutes. And another thing to note now with the database, and as I mentioned earlier, this work is more reproducible and applicable in other settings because you can just change a couple lines of code to retrieve the same type of information, but let's say for different states. Okay, so what we have here now with the database, we are able to compare several cities across different years and include many different family types. And prior to the database, this was not possible. We were only able to look at one specific year and one specific family type across several cities. And now, because of our detailed documentation and improved workflow, we are now able to reproduce these analyses in different settings. And one analysis of interest that we conducted was comparing graduate student salaries to the Self-Sufficiency Standard. And specifically, we were interested in looking at single adult PhD student wages to the Self-Sufficiency Standard across across 2 different universities, across 2 different years. And as you can see, it's not enough. So what we have on the left here, What we have on the left here is the self-sufficiency wages for King County, Seattle for a single adult. And then we have in the gold UW's PhD student wages. And on the right, we have the self-sufficiency wages for the Los Angeles County for one adult in purple. And then we have UCLA PhD student wages in the light blue across 2 different years.
So we also conducted additional analysis in terms of gender wage gap. So since the earnings gap between men and women varies by state, how is the gender wage gap impacted by the difference in the cost of living as defined by the Self-Sufficiency Standard data? So we conducted analysis for 3 household types where there is one adult, as you can see here, one adult and one preschooler, and another one is one adult, one preschooler, and one schoolage. As an engineers, we were interested in analyzing the cities that are hubs for technology. Thus, we chose King County, Seattle, and San Francisco County, which encompasses itself only San Francisco City. From the analysis, we found that both female and male adults living alone can afford themselves in both cities. However, when a child is involved, single mothers cannot afford one preschooler in both cities. So while single father can actually afford one preschooler plus one schoolage in both cities, so this actually clearly shows that there is a greater impact of gender wage gap in cost of living.
So we also, according to this database, we are able to create a live interactive website, a map, which if you click, it will compare some kind of stuffs. And this is the first ever we could compare the self-sufficiency standards and the poverty line nationally. And if they are empty of the polygon, which means we did not collect the data of the state, which is empty. And the area with deeper purple, and which indicate the higher percentage of the population below the self-sufficiency standards. And when we click one polygon of a state, it will pop up the information of the percentage of population under the self-sufficiency standards and the percentage of the population below the poverty line on the top right. As take Washington state as example, like around 20% of the population below the self-sufficiency standards, but only around 6% of the population below the poverty line. This is also echo of the claim we have before. There's a big gap between the self-sufficiency standards and the poverty line. And moreover, if we zoom into one state, let's see, we just picked the Puma area, which is the University of Washington located. And the percentage of self-sufficiency standards and poverty line will, for this specific Puma, will pop up on the top right. Yes, this is kind of mirror here. Take an example for this area, if like 2 adults and 1 infant, maybe like a graduate student's family, and the self-sufficiency standards is around 78,000 for enough because self-sufficient, but the poverty line only claim 22K, which is much lower than the self-sufficiency standards.
And so because this is an ongoing contribution to a long-term project, we wanted to envision how the database will live on in a visual and accessible format. So this is a dashboard designed for a general audience to explore the standard in a more digestible format. So what's made easier here is that you can clearly see the database structure, the table you're accessing, and then you can explore the standard for specific states, counties, years, and family types. And then after that, you can easily drag the values to what you would want to visualize in a plot. And while this is just a concept design, it can be handed off to the Center for Women's Welfare to build as the database gets further developed. And that is the end of our presentation. Thank you to our sponsors. And if you would like to interact with the national comparisons map that Chang shared, we have a tiny URL at the bottom.
So the first question, this person is wondering how data quality check for QA is streamlined, and is there a process developed for that as well?
Can you repeat the question?
Yeah. How data quality check is streamlined, and is there a process developed for that as well?
Okay, so the question was, how is data quality check streamlined, and was that process? And is there a specific process for that? I know in terms of like creating the database and understanding it, like we did checks for like columns and column values. And I know we included some handling of data errors or certain complications in the data within our code, and specifically with like converting certain values into like what was needed into the database. And we also include like in our repository, we include that, and also a pre-processing file, which handles and standardizes all the columns and data for the database. So I hope that answered the question. Maybe a question.
Yeah, this is amazing. Like, very applicable. My many students stepped out, but this type of data from we actively need this kind of data. Like, I was yearning for this so much. But I'm doing how often is the data refreshed? Like, I'm going similar stuff from 2020, and knowing that like a ton has changed as far as in 2 years. The data, just kind of curious about the freshness.
Okay, so we had a question on how often does the data get updated?
So it's kind of depends on like which data source you are talking about. Some data may applied like refreshed every year. Some data source kind of applying just based on the adjustment of the inflation. So it's like just depends on like which data source you are referred to for the specifically. So for the self-sufficiency data set itself, like we update every year. Yeah, no, for the map. It's public, but we did not publish it yet. Yeah, it will be. It's
It's a long list.
So yeah, you can summarize that exchange.
Yeah, you can summarize.
Basically, there's the answer to the question from Annie was basically that the data gets updated collectively. All the partnered states their data gets updated collectively every 3 years. And all the data is available that we use in the database online at Self-Sufficiency Standard.org. Do we have another question?
The thing that strikes me about it, though, is that the procedure on the left I could read as a recipe where it sort of understates like on the right requires me to know and be able to read and be able to use code. And I guess I am just interested in what your experience has been introducing these really powerful tools to a research community that might not have a background.
Yeah, so the question was referring back to the slide. Do I want to change back to the slide? Okay, referring back to this slide of comparing the workflow before and after the database. And specifically on the left, you can kind of see all the steps and it's kind of like straightforward. But the question was, how has our experience been on with this updated workflow of having others with different technical backgrounds use the database?
Yeah, so basically the question was about the complexities. So we have two different stages here on the right, on the right side. You can see that there's like, it takes about 3 to 5 hours to interact with Excel, and then try, if you want to compare it to different cities, it takes some time, right? However, like on the right side, it takes about 5 minutes just interacting with the database and calling it, like, let's say on Jupyter Notebook. The analysis that we have actually conducted, like that we show like three different analysis, we use the database itself. So what we have a one package. What we do, just import SSS database, and we like run a SQL query on that, and it's really easy to interact on Jupyter Notebook. That's why it takes like really 5 minutes to run the code. We are currently working on documentation, which we aim to finish it up by the end of the week and handle to the general public on GitHub and on the website as well. So like anyone without like a technical expertise can just go and like follow the direction and like work on that and just get everything done in 5 minutes. Yeah.
And and just to add on to what Aziza just said, we also went through, we had Alyssa from the Center of Women's Welfare at UW try setting up the environment and their computer to get the database running, but I don't think we've gotten through creating the database and then exporting data. So we're still in that process. Yeah. Oh, from online, do I click?
You received any specific feedback about how useful the database is for people with little to no technology experience?
Okay, so the question was, have we gotten feedback from those with little to no technical experience on using the database? And as of now, we do not. We've gotten feedback on setting up the environment, specifically like terminals and creating the database, but we have not gone through the process of inserting data and extracting data. So by the end of the week, we should have our documentation done and code running to get some tests going. Thank you.
Really nicely done. All right, tracking poverty team, come on up.
I can't even. Yeah. I don't know. Okay, let me just do that first. Oh. It says file is an owner's trash.
Here, we have the, we can, should we?
No.
Is this the right one?
No.
Is it in the finished list?
No. This is not, no, this is the final one. I just didn't have tracking poverty like full name, just for peak.
Okay, so that's the right one?
Do you want us to? Huh? I don't know what's wrong with that though. I think it's maybe because you made it as PowerPoint. Should we download it real quickly?
No. Yeah,
Oh,
no, it should be, it was fine early.
Okay.
Yeah.
Okay, it's fine now.
Okay, I don't know what that was.
That's weird. Okay, thank you. A little bigger. Thanks. Yeah, you're welcome.
All right. Can I start? Okay. Hi, everyone. We are the Tracking Poverty team made up of Jawen, myself, Bethlehem, Isan, and Elliot, and our project lead was Jenny, and our data scientist was Jessica. So we're going to just give you some introductions and then go into the two approaches that we did, looking at one looking at multiple definition at 1 month, and then the other one looking at time looking at one definition across time, and then looking at and then ending with future work. So our purpose was building households and families out of individual level data. So why do we care about households? Let's say we have two individuals. One has an annual income of $15,000 and the other one has an annual income of $100,000. If they were unrelated, one would be under the poverty line and the other one would be considered non-poor. But if they were related, they both would be considered non-poor. Poverty is a household level construct. It looks at pooled resources. So when you think about questions about poverty, we're thinking about who is sharing those resources. And this would allow us to answer questions such as like the impact of the Seattle minimum wage, which and its impact on the poverty rate, which is one of the longer term goals of this project. So what is a household? A household is defined in many ways. The census defines it as a people that occupy a housing unit, and they can be related or unrelated, but kind of puts it into two categories of family and non-family households. Additionally, we found when we were like looking at different organizations, one defined it as people that buy groceries and cooks together at a residence. So it's really nuanced definition across people. And then socially, there are like our age, our marital status, our immigration, race, class, really influence how we think about our own household, our family. So our goal was really to think about how can we get to a point of this is a resource sharing unit or economical unit that really represents as much the complexities of society as possible. So here we're looking at residence as a physical household, family is like a relational household, and household as defined in multiple ways across the spectrum of residence and family. So we use the WMLAD or the Washington Merged Longitudinal Administrative Data Set, which was created to examine employment and earning outcomes. And it got information from across 6 state agencies, about 10 million people across 96 months. And it was not collected for research purposes. And that's something important to know. And it also, like, some agencies cover some subpopulations more than others, but collectively they give us a really, it was very informative for us to know who was in the data and also consider who else was missing from the data as we went on to do our analysis. And then on the second section, we looked at previous work by Jenny and many of her colleagues, and when they looked at, like, we focused on these two that they looked at, which were the recorded addresses, which looked at sporadic address records from months that people interacted with the agencies, and then used that to create estimates and replace the missing addresses across the 96 months to get more the likely or imputed addresses, which we then used as our starting point to kind of improve upon using 2 different methods, the point in time and the longitudinal method. So while we were doing this, we had to recognize these are people that we are talking about, and we were always trying to think about the ethical considerations with using administrative data. We were always trying to think about what are the different definitions that would consider the atypical households as best as we could, as well as thinking about using the enclave and layers of anonymity to maintain security and privacy of the data, and then thinking about having detailed documentation and holding ourselves and each other accountable to use this data for public good, but as well as consider this is people that we're talking about. So this is what we saw in week 2. There's a lot of the whole big chunk of the summer we just used to try and understand what was there. We had some guidance, but really we spent a big chunk of it trying to understand what the structure of the data sets, distinguishing between the important variables and non-important, for our purposes. And then from that, we kind of created a schema to really pull out the ones what we wanted to focus on, which was focusing on demographics, the imputed address codes, last name codes, and social services, and kind of just looking at the relations between them, get rid of redundant information, and then cleaning the data, and then putting this into a database that we could use to look at households, as well as future people can use.
All right. So we took 2 main approaches to creating households. The first we call the point in time approach. And in this, we consider just 1 month of data at a time, and we add on 1 variable at a time. And at each stage, we subtract out the households that are clearly defined enough, and we don't need to consider them anymore. So we started with address information, and then we considered last names in 2 different ways. And after I talk about that, Jawan will tell us about our longitudinal approach, where we consider address information over multiple months. So we take our population and we start by grouping them by address, both the recorded addresses and the imputed addresses. And when we do so, everything becomes more clear. In this case, you can see 5 people share an address identifier in our data at a given month. And our first definition uses this residence as its only input. And the output is that it's a household. So this sort of follows the census definition where people who live together are a residence or household together. And this actually is the basis for our other definitions, in that only people who live together at the same time can be a household. The census works this way, and so do the rules for different anti-poverty programs that we have data on. But what this definition doesn't capture is, are these people roommates or are they family? If we assume that they pool income together, we could miss some people living under the poverty line. So we want to get closer to measuring a family, or more accurately, a resource sharing unit. And to do so, we try to infer relations from the data. One limitation of this, we are looking only at a single address at a time. And so we're not identifying resource sharing with dependents who live elsewhere, even though we know that that takes place. But instead, we're dealing with cases where people live together and may not be sharing resources. We have limited data options to choose from here. We don't have marriage licenses or much information on children. And we have to be really careful with using demographic data like race and sex, which covers almost everyone in our data set. But inferring relations based on these categories would just reinforce heteronormative, racially homogeneous traditional family notions. So instead, we look at last names. Why? If people share a last name and they live together, we're pretty certain that they're family. And we have one in our data for almost everyone. We also found that 63% of the naive households have only one last name. This does include people who live alone, but it's still a pretty large part of our data that we were able to take out of the picture. So now we see we have 2 clear cases. There's one last name in the residence, or there are multiple. For the first case, we preserve the naive definition and we consider them completed, which reduces computation time in our further exploration and decision making. For the second case, we take 2 approaches. The first is deterministic. And in this approach, we split the multiple families up at the single residence into separate households by last name. However, we know that many families have multiple last names in them. So to address this, we use probability to decide between the 2 options, keeping them together or splitting them up by last name. And we do this with a weighted coin flip. We weight the coin based on the census likelihood that a residence is a family or not, by household size and region. For example, in this case, we would look at 5-person residences in counties A and B, and maybe county A has 80% of them as families and county B has 20% as families. So those are the weights for the coin flip. And we could get a lot more granular with these probabilities, incorporate age information in census microdata, tailor to more specific cases with the number of last names in the household. But this is as far as we got, and the code is set up so that it's easy enough to adjust these probabilities in the future. And here's a quick recap of our household definitions. We have naive co-residence and last name definitions, both deterministic and probabilistic.
Thanks. Hi again, this is Ihsan. So sorry for your eyes to making you look at the table with a lot of numbers. It's my bad. So what we're gonna do today, right now by my section, I'm gonna show you some of the distribution of how households differ based on our definitions, and we're gonna compare the census data. But I need to tell you that there's not an actual grand truth comparison for this kind of research. So we can test certain definitions. Certain definitions do well on this kind of comparison to census, certain does not well. The whole idea is depends on a research question, and the way you want to calculate poverty is which definition or what type of way to look for. So in this case, we only compare census. I'm sorry, I have to repeat. So this is for all Washington states, for all families, all households, whether a family or a non-family, and their distribution across household size, 1-person families, 2-person families, to 7 and plus more. The reason for 7 plus more is just came from census. And so in order to make the comparison, we have to lump them into the same category. So what we understood is here. So if you remember the method, if you remember the methods, the naive co-residence, basically putting people who live in the same time and address into each other. This should make the census process as close as possible. But the problem is here, as you can see in the first household size, we have overestimated these people in terms of percentages. And the reason for that is most likely we don't have the children data. Here's an example. We see a one person, maybe a single mother with a child that we don't have in the data. We think they're a one person household, but in reality, they might not have to be, or they might not be. But in general, as you can see, and especially in larger household sizes, the percentages are a lot closer and the counts are a lot similar, especially this is like very similar in 3-person households. I don't have an exact reason why 3-person households are like better off than 4, probably just chance. But as the number of household sizes increases, these numbers, so you see the drawbacks, pros and cons. But as Elliot mentioned, the other thing we need to decide, okay, we can divide people into smaller groups, but how can we decide whether they are families or resource sharing units or not? And that's the second comparison. And this time, instead of looking at, unlike here, the all family and distribution of across sizes, we are looking at the census, I'm sorry, I should have said decennial census 2010. Census is not one thing. There are a lot of census data. It's US, because our data covered from 2010 to 2017, the only decennial census data with exact counts but not uncertainty came from 2010 census tables. And moving on, we look at the family, what census called family households on the first axis in here. So these are the percentages of, and that's why we don't have a 1-person household, because census doesn't label 1-person households as families. And the first thing, if you remember, the last name, if you just disaggregate co-resident people who are co-reside, staying together in a given month, you will have a lot of 1-person or sorry for the echo, 1-person family is going to pop up because you don't know you haven't done anything with them. But that has some advantages that you will never, at one point you will get very granular, but at the other thing, you will probably miss a lot of people who can be a family but not share a last name. So the good thing in here, when you take just the mere tract level, tracts is a geographic unit, is smaller than the county, but bigger than the neighborhoods. You can refer them as blocks, neighborhoods, so it's bigger than neighborhoods. And you can reduce the discrepancy, and you can have a better distribution, and they can match better. And and even this simple taking up the probability, adjusted probability, once you label the ones that you already know of, the numbers match slightly better. And this, but as you see in here, as the size increases, and as you can also see in here, as size increases, what you see in here, you take 1 or 2 people households, probabilistically put some of them as higher families. Actually, we're not putting them in here. We put them non-families, but the ratios change so that you have a better distribution. Sorry, I should have been more clear about it. But the case in here, what happens to 1-person families? We will have much more discussion when Javan talks about it, but I want to show you an evaluation of this. This is Seattle metropolitan area. And this is, so this map shows you whether we overcount represented as red, whether we undercount. Right, okay. It's kind of weird. Whether we undercount based on blue. So the color should be the reverse order. I was confusion. And we have some form of a vague confidence interval. Basically, if we miss between 2.5% below and above, we count it as, we say it's within the error range. So you see them as white. And in most of the Seattle, you can see that they're red, so we overcount 1-person households, which makes sense because I have to remind you, this is for just co-residents, and this makes sense because we have missing data on children. But when you go back to the downtown Seattle area, where we know that from census, we know a lot of 1-person households leave, we are undercounting. Even with a definition that we hoped our count than undercount, we are still undercounting in the 1-person families in the downtown area. And this where we see the likeness of one point in time approach, and we will introduce you why we should look at this problem longitudinally.
Additionally, we look beyond point in time and incorporate longitudinal household changes to improve our imputed addresses. To begin with, we compare the distribution of households by size using census and our naive co-residents from WMLAN dataset, and found that we overestimated one-person residences and underestimated the others. To explain why this happened, we looked into specific scenarios regarding these one-person residences. In the first scenario, we observe one person living alone for a few months and then start to live with others within the same address. This is likely to happen when the added person is a child who interact with government agencies less frequently than adults. For example, only when the child registered to vote or get their driver license would they leave an administrative record into our data. In this case, we want to make a revision to reflect reality. For the second scenario, we observe alternately appeared pattern of one-person residences and the other multi-person residences that the person belongs to. We believe that these frequent movements into and out of the same address are likely to represent an imputation error, and we want to revise these one-person residences accordingly. For the third scenario, we observe two persons living together for a few months, and then they start to separate from each other and reunite again in a new address. We believe this corresponds to the case where members of a household move out at the same time, but their addresses were not updated accordingly. In this case, we want to pull these one-person residences together in the transition period. However, here is a case we don't want to make a revision, which is when the two persons who used to live together for a few months, and once they move out, they no longer live with each other. We want to leave their observations as they are, which means we only want to make a revision when the co-residence before matches the co-residence afterward. Taken together, we want to revise the one-person residences, taking into account the following scenarios: lack of interactions, imputation error, and moving in and out. After implementing this modification algorithm and removing duplicates to make sure that each person only appears once in a given month, we found that the proportion of one-person residences went down to 31%, which looks closer to the census data. So to summarize what we have done throughout this program, first of all, we created a relational database for future WMLAN users with all data in a clean and well-structured format. And we also applied both point-in-time and longitudinal approach to derive and improve household and family identifiers. We believe our workflow and data output can be used for future researchers to answer questions at the household level. And admittedly, our work is subject to some limitations. One of the limitations is that we only apply the longitudinal approach to households of size 1, and in the future, we hope to extend the logic to households of larger sizes, while integrating point-in-time family information and longitudinal corrections. Moreover, we hope to incorporate other information such as social networks, demographics, and anti-poverty programs to capture a diversity of households. In the end, we want to thank everyone that supported us and our work throughout this program, and we look forward to your feedback.
Hector? I had a question back to the part that you saw showed, specifically.
Which one?
Yeah, the one before that. Okay. Yeah, I'm just trying to understand what are the values specifically for each of the columns, because I know if there's.
Okay, sorry, it's my. And Hector is asking the more clarification about what values are in the table. And thanks for the clarifying question. So these are the counts of any, so this is a category of household sizes. And for any each category, how many people, households, I'm sorry, census counts, how many are last name deterministic last name classification counts as households, and how many are left when we have the probabilities. And but the percentages are only calculated based on the column totals. So because the thing is, we are looking at 96 months, and census only looks at the first 2010. So the counts are going to naturally change. So there are two things we need to care: how many people we are missing, especially in crowd areas, and also how the distribution within a definition really changes, so that whether we can catch whether there's like an odd behavior or so on and so forth.
scale of the problem, like how many households and what the different probability. How many households?
Sure. Oh. I have a graph for this. Oh, yes, the question is about the scale of the problem with the households and how many of them have different last names. So I made this graph. And you can see like more than half of the 2-person households have only one last name together. Almost a third, 25-30% of the 3-person residences have all one last name. So what we were doing with the sort of 63% that we were able to take out of consideration, like the green people in the little picture, was like the first bar in each of these plots for household size. And when I was talking about how we could refine what we're doing going forward, for example, if you think about like a 4-person family or 4-person residence, if there's 4 different last names, we should be much more likely to consider them separately than maybe if there's 2 last names and 3-person share a last name, 1 doesn't. That's very common in families. And obviously we don't want to make too many judgment calls about what could or couldn't be a family, but in terms of who we're sure of or more sure of, that's something we could change.
Can you also give an example of a covariate so I can repeat it?
The partner is more common or less common for blended families. So I'm just wondering if you're, as part of this, considered some of the things that might drive the phenomenon of different last names that are still.
Okay, thank you. I'm just repeating the question. So the question is about what are the other cultural and demographic outcomes or the things that we missed about using last names in our classification or in one of our definitions, and what are the things that we did to address this problem?
Okay.
You worked before.
You want? Yeah, I could go for it.
Okay. So we did think about that. And I think we're hoping this could be the beginning of it, and then adding on more like demographic or other cultural things that could, or other variables that we have within the administrative data set to like kind of tie to cultural, using like demographics that may assist in clarifying those. So I think because right now the last names are like in codes, there's no telling you like this is a certain type of culture, or, like there's no, right now it's not deterministic, it's not actual names. But like later on we're hoping to like use other factors to help that could tie to the last names to make it more, yeah, you can add to it. Yeah, but yeah, so I think it's a first layer of it, but definitely we've been thinking about refining it as we go on, because it's too small right now. Yeah. But,
sorry, I was asking to Elliot just like I'm so sorry. And another thing, we are never saying that the people we couldn't identify are not families, but we want to use, at least there are people that we can identify by last names, and as much people we define, as that means there are less people left to do it, and as less people left, you can do more, the computation time easier, the work with the data easier. So we're not saying that the people we couldn't identify are not families, and so this is a room for, but the ones we have a last name and a co-residence, we are much more confident about they pull resources and are in the same poverty unit. So.
oh, sorry. Okay.
One of the things that I was curious about is for the longitudinal approach, and how did you sort of find the imputation error, and how often was that? Because that's really difficult
Yeah. Sure. The question is how we fix the imputation error by incorporating the longitudinal household changes. So for example, in this graph, we can see that the problem comes from one person residence. We overestimate them. And we then look into some specific scenarios regarding why this is happening. The first scenario is the case I discussed, which is lack of interactions, especially for children. So to fix cases like this, we first filter the cases where the people is below the age of 18, and we see if this one person residence is a subset of the next different co-residence. If so, we fix the one person residence as the next different one. And for the second one, we don't want to fix is a frequent moving out, which we believe to represent an imputation error. In this case, if we observe the pattern that one person residences and this multi-person residence that the person belongs to alternately appeared multiple times, we want to fix these one person residences as a neighboring one. And for the third case, which we call moving out case, happens the transition period. So in this case, if we identify the case where for the one person residence, the previous co-residence is distinct from the next co-residence, we want to fix the middle in the transition period to be the previous or the next. And we also keep in mind that we don't want to make a revision for cases like this, which is persons living together no longer live with each other once they move out. So we also keep this in mind. Yeah.
The general idea is that imputation was done for the individual. And so we have the addresses sporadically that they showed up in the data, and then it sort of estimated when they moved between them. But since we're looking at multiple groups or multiple people in a unit and we can see their relation to each other, the idea, for example, in this case is that if we know that these people are a family, we know that they probably moved at the same time. And so we have a lot of ideas for how we would maybe revise imputation, but it is very complicated. It was, as you know, done prior to our project, and we used the information we had the best we could, but Jawen's modifications were really useful for us.
There's a question from the remote participants. Someone asked, sorry if I missed this, how did you deal with spelling errors and last names common in administrative data?
Yeah, so we did not have oh, sorry. One question was, how did we deal with spelling errors in the administrative data? And when we got it, we didn't have any actual names. We had codes for names, addresses, unique IDs. So we didn't actually know their names. It was just given a number. So there was no error in that sense, if that answers.
Yeah, the data was, I think, cleaned and put together by some people over at DSHS a little while ago, and we got it already de-identified and anonymized and everything like that.
And let's get a round of applause for. Yeah, can you just pull up the? Okay. Yeah, so if we can just get a round of applause for all of our teams, all of our student fellows. This is a tremendous amount to accomplish in 10 weeks, much of which is also spent just getting to know each other, getting to figure out what the problem space is. These students all come from different disciplinary backgrounds, different areas of expertise. And so it's really a unique program. And I would just say we're really proud of all of you. I'd also like to acknowledge the eScience data scientists and all those folks who came together to provide mentorship from the project leads to other data scientists and other people on the UW campus. This program really ends up involving 50+ people that come together in terms of providing and supporting career panels and Slack channel discussions and giving talks to this community. So it really is, I guess it takes a village to run this program. I definitely want to thank kind of first and foremost our program chair, Anissa Tanweer. This program really wouldn't happen without Anissa, and her leadership has really allowed this program to evolve and allowed us to do crazy things like going remote and then do crazy things like coming back and trying to be hybrid. We never like to settle and just stick with something we figured out. I'd also really like to thank Emily Keller, who's just a fantastic program coordinator for this program, and the eScience administrative team, particularly Jenny Holcomb, for making, I think, all of the students, both those in the virtual space and in the in-person spaces, feel very welcome and well-fed. So thank you to everybody who has supported and participated in this program over this year. I did want to note, and this slide represents it, if you liked what you heard today and you're thinking, how can I get more of this? We are actually running a conference coming up in a few weeks here on the University of Washington campus, but also available virtually, called Learning and Doing Data for Good, a conference for academics and their partners. And this brings together students in similar programs at other universities within the United States and also the UK and Canada to come and do just this kind of showcasing, highlighting work that is really focused on social impact and using data intensive techniques. There's not a great forum for this anywhere else that we're aware of in quite the same way. And so we wanted to give the students an opportunity to meet other students who are active in these programs, both currently this year and historically. So if this sounds interesting, please come join us. We'd love to have you participate. Lastly, I'd just like to say thank you to all of you in person and online for attending this event. This is exciting for us every single year. We do a little fingernail biting this last week, right, everybody? But look what you all put together. It's really impressive. And this takes a lot of commitment from all of you and many others involved in the program. So for those online, we say goodbye. We wish you were here because we can all now go out and join a reception. We will celebrate with you virtually or in spirit. So thank you all. And the reception is just across the court.